Hello. In the last lecture, we have already seen the modeling of induction machine in stationary reference frame. We will just recapitulate what we have done in the last lecture. Model of induction machine in stationary reference frame. Now, we can write down the equation for the stator and the equation for the rotor, and then we can develop the torque equation, and from the torque equation we can find out the speed. So, this goes in an iterative process. So, let us write down the equation for the stator. So, this is VDS is equal to RS IDS plus P psi ds. The stator is stationary, hence the stator does not have any rotationally induced EMF. And we can express the flux linkage. This psi ds is the flux linkage in the d axis stator. So, we can express that in terms of inductance and current. So, that is equal to RS IDS plus LS P IDS plus LM P IDR prime. IDR prime is the current referred from the primary side. And similarly, we can have VQS. VQS is equal to RS IQS plus P psi QS, that is equal to RS IQS plus LS P IQS plus LM P IQR prime. So, these are the two equations for the stator. Now, we need not simulate the zero sequence equation because the zero sequence equation does not take part in torque production. So, for the calculation of the machine torque, it is sufficient only to write down the equation for the D and Q axis and find out the corresponding currents and evaluate the torque. Similarly, for the rotor, we can write down the equation for the rotor here. VDR prime, RR prime, IDR prime plus P psi IDR prime, and the rotor will have a rotationally induced EMF, and the rotationally induced EMF will be a function of the speed of the rotor. So, that is plus omega r psi QR, and we can again express this in terms of current only, IDR plus LR P IDR plus LM P IDS plus omega r into LR IQR plus LM IQS. Similarly, we can write down the Q axis voltage, VQR prime equal to RR prime, IQR prime plus P psi QR prime minus of omega r psi IDR prime. This we can express in terms of the currents only, RR prime IQR prime plus LR prime P IQR prime plus LM P IQS minus of omega r LR IDR plus LM IDS. Now, these four equations, when we solve, these are four simultaneous differential equations. Now, we can solve this numerically. We cannot have any analytical solution because the voltages are sinusoidal, but sometimes the machine is also fed from an inverter. When the machine is fed from an inverter, the voltages are not sinusoidal, and furthermore they can be any function of time. So a closed form solution of these equations is not possible. So we have to take the help of numerical method. One of the popular ways to simulate this differential equation is the Runge-Kutta fourth order integration technique. So we can use Runge-Kutta fourth order integration technique to find out the values of IDS, IQS, IDR and IQR, and these values will be useful for the torque calculation. Now this equation, those that we have written here, we can express them in the form of a matrix. So we can just write down these equations in the form of a matrix: VDS, VQS, VDR and VQR. And here we have the impedance matrix, and then we have IDS, IQS, IDR and IQR. Now this impedance matrix is a 4 by 4 matrix, and we can fill up this matrix from the previous equations. We can also fill up by inspection. We don't have to remember the various elements here. By intuition we can fill up each and every element of this matrix. Let's see. So we have 4 rows here, and 4 columns. Now this is RS plus LSP, and this one is LMP, and the stator doesn't have any rotational induced EMF, so we can make this equal to 0. For the Q axis stator, this is RS plus LSP, and this is LMP. Again we have this element 0, because in the stator we don't have any rotationally induced EMF. In the rotor we will have the resistance drop, the rotor self inductance, and then we have the coupling from the stator side, and these two are the speed induced EMF terms. So we have omega r here and omega r, and this will be coupled to IQR. So we have LR prime in this case, and this is LM from the stator side. And for the 4th row, that is for VQR, we have RR prime plus LR prime P. Then we have coupling from the stator side. Then we have the rotationally induced EMF minus omega r LM and minus omega r LR prime. Now this equation is a key equation for solving the differential equation of induction machine, and this we can also represent in a symbolic form. So if we represent this in a symbolic form, we have the following equation. So V is equal to an R matrix, and I plus L is the inductance matrix, Pi plus omega r, a G matrix, and then we have I. So this matrix equation can be written in the following form. Here V is a vector, V is corresponding to this vector, I is corresponding to this vector, R is the resistance matrix, which is a diagonal matrix having the elements RS, RS for the stator and RR prime and RR prime for the rotor, and this L P is the matrix associated with the derivative of the current. So this matrix can be easily evaluated. Those elements which have got derivative terms, they are clubbed into L matrix, and those elements which has got the speed term is clubbed in the G matrix, as you have already seen in a Cron's primitive machine model. And this G matrix can be easily identified. So we can write down what is the G matrix here, because this G matrix is useful in calculating the torque of the machine. So from this 4 by 4 matrix we can see that we have got this element is having omega r term, this element is also having omega r term, this is having omega term, and this is having omega term. So this G matrix will have 4 elements. So we can write down this G matrix. And once we evaluate this G matrix, we can find out the torque. Torque is equal to P by 2 I transpose G and I. Now we know that we have a 3-phase machine, and the DQ model is a hypothetical model. It doesn't really exist. We are simulating a 3-phase machine by means of a 2-axis model. So when we are finding out the torque, we should be careful that we should get the torque back to the 3-phase machine torque. And we have already seen that the transformation that we have used, the transformation for the stator and the transformation for the rotor, has got per phase power invariance. So if we have 2-phase machine, the power of the 2-phase machine is 3 by 2 times of, if you have a 3-phase machine, the total power is 3 by 2 times the power of the 2-phase machine, because the per phase power is invariant here. So if you take a 2-phase machine, you just have 2 phases. If you take a 3-phase machine, you have 3 phases. So if you convert the power of the 2-phase machine into the 3-phase machine, you have to multiply by a factor of 3 by 2. So here we have to multiply, in this case, a factor of 3 by 2, because our model is a 2-phase model or a 2-axis model. Actual machine is a 3-phase machine. So if you want to convert it back into the torque of a 3-phase machine, you have to multiply 3 by 2 in this case. So the torque in this case is 3 by 2 into P by 2 is the pole pair I transpose G into I. So we can simplify this, and if you simplify this, we can pre-multiply and post-multiply. Let me just write down the final expression. The torque is given in the following form: 3 by 2 into P by 2 into Lm IDR prime IQS minus IQR prime IDS. So it means if we know the various currents, we can evaluate the torque of the machine. So how do you simulate this equation? Now this equation can be simulated in the following fashion. Now we can evaluate what is this LP. LPI is given as V minus of Ri minus of omega r Gi. If you see this, we are just trying to rearrange this equation. So we are taking this term to the left hand side and trying to evaluate what is LPI. So LPI is given as V minus Ri minus omega r Gi. Now ultimately what we need is the current. So if you want to find out the current, we should know the derivative of the current. So Pi is equal to L inverse of V minus Ri minus omega r Gi. This is what we have, and this can be solved using Runge-Kutta fourth order integration technique. So we solve this by we can use Runge-Kutta fourth order integration technique to solve this equation, and once we solve it, we can find out the values of the various currents, and from the currents we can find out the torque, and for the torque we can also find out the speed. Usually when we simulate a machine, the electrical variables vary at much faster rate than mechanical variables, and hence in this particular case the currents IDS, IQS, IDR and IQR vary at much faster rate than the speed. Speed is a mechanical variable. So we can take this advantage of this particular property and we can simulate the current equation separately and the speed equation separately. What we are trying to do here is this, that the 4 equations that we have, this is basically 4 equations we have, IDS, IQS, IDR and IQR. We can solve them simultaneously by using Runge-Kutta 4th order technique. And then when we come to the speed equation, we have the mechanical variable and that vary much slower than the electrical variable. So while simulating the electrical variable, we can assume omega r to be constant. And after we obtain the torque, we can simulate this equation by linear integration technique, and first order is sufficient. We can just have first order linear integration, which will be much accurate to give us the value of speed. So we can find out the speed from this equation, and we know the torque and the speed. So once we know the torque and the speed, we can plot the torque speed characteristic of an induction machine. Now you will be surprised to see that the torque speed characteristic that we obtain of an actual machine is much different than what we have studied in the previous courses in electric machines. In the previous courses in electric machine, if you see that if you plot the torque speed characteristic of an induction machine, TE versus omega r, you will see a curve like this. So this is the synchronous speed, and this is your torque axis, and this is the speed axis. Here the speed is equal to 0, and this is the nature of the torque speed characteristic, and this has been obtained by assuming steady state equivalent circuit. The equivalent circuit, which you have already studied in your previous courses in electric machines, especially in the undergraduate second year level, gives the torque speed characteristic of a steady state machine. The machine is in the steady state condition. But here when we are simulating the machine is actually the actual machine. It is basically proceeding from the transient condition to the steady state condition. So if you take t equal to 0, your starting time for the simulation, and take some delta t for the simulation, and you have a finish time Tf, and we can simulate this equation. The response that we obtain is the following. Now we would like to call this to be a steady state torque speed characteristic. Now if you have an exact simulation starting from rest, the torque speed characteristic will be something different. We can first plot torque versus time. We can plot speed versus time. We will see that the torque is not a smooth variable, it is basically a function of time. It oscillates like this, and finally if you have no load condition, it settles down to TE equal to 0. If you assume that TL equal to 0, as if the machine is being started from the stalled condition without any load, it accelerates and reaches the synchronous speed or close to the synchronous speed. It is called free acceleration. So when we simulate the machine under free acceleration condition, there will be torque oscillations initially, then finally it settles down to the final speed where the torque is equal to 0. In the steady state, it operates under no load condition. What about the speed? The speed gradually increases and finally reaches the steady state value here. And if we plot the torque speed characteristic under free acceleration condition, it is something like this. So in this case, we have exactly the plot that's available as the machine is starting from rest to the full speed. Now this is because of the fact that the machine is being simulated through the transient condition. And when we energize an induction machine, in addition to the AC component of the current, there is a DC component of the current, and the DC component produces a DC flux, and the DC flux interacts with the rotating flux to produce a pulsating torque. So that's the reason why we have torque pulsation as the machine starts from rest. So this can be verified when we simulate the machine in the DQ equivalent circuit, in the DQ model, taking into account the transient condition and reaching the steady state finally. So this is an interesting thing which can be seen in the simulation. Okay. Now with this, before we proceed further, we would like to introduce a concept of reference frame. Reference frame is extremely important because when we analyze the machine, we take a reference frame as per our requirement. It can be a stationary reference frame which is stationary in the space. It can be rotating reference frame which is rotating in the space. And this reference frame is not chosen arbitrarily. They are basically chosen depending upon the need of a special control theory or need of machine simulation. So we would discuss in this case reference frame theory. So what we have here is the following. We have a set of ABC system. This is phase A, phase B and phase C. And we would like to transform this into a DQ system. But the DQ system need not be always stationary. This may be rotating at certain speed, any arbitrary speed omega. So we can say that when we convert this into a DQ system is always orthogonal. This is my D axis and this is the Q axis, and this angle that is subtends with the A axis is theta, and the reference frame is rotating at a speed of omega radian per second. So this reference frame is not stationary, is rotating at a speed of omega radian per second, and this is called a rotating reference frame. Now when we transform the variables from ABC into DQ, we get the following equation. Now we have FD, FQ and FO. These are the variables that we have in the DQ reference frame. FO is the zero sequence component which can be present in general when we have an unbalanced system. There could be a zero sequence component. Now this FD, FQ and FO can be obtained from FA, FB, FC. So we have a transformation here. So we can use a transformation in this case, and this transformation will give us FD, FQ and FO from FA, FB, FC. Now what are these FA, FB, FC? They could be voltage, they could be current, they could be flux linkages for a electric machine. So we can say that F can be voltage, can be current or flux linkage. Now when we transform this ABC into DQ, we will take the help of this transformation, and the transformation can be easily found out. What we can do here, we can project this A onto D axis, project this B onto D axis, project the C onto D axis and calculate what is the equivalent FD. Now if we do this simple exercise, we will get the following result. We have cos theta 1, cos theta 2, minus of sin theta, minus of sin theta 1, minus of sin theta 2, half, half and half. So we have a multiplication constant here, that is 2 by 3. Now this 2 by 3 is multiplied in this case to keep the per phase power invariance. When we are transforming the ABC system into DQ system, we have to be careful that this does not alter the system parameter, neither it alters the various variables of the original system. Say for example, if I have a 400 volt 3-phase system, the per phase voltage is 230 volt. Now if I transform this into a DQ system, the per phase voltage should also be 230 volt. Otherwise, there will be a discrepancy and extra work has to be done to calculate this transformation. Similarly, if we have a 3-phase system, the 3-phase current, per phase current is 10 ampere. In the 2-phase system or in the DQ system, the per phase current should be also 10 ampere. So we have to take such a transformation which does not change the per phase power. So this is based on per phase power invariance, and that's why we multiply in this case 2 by 3 so that per phase of the 2-phase system or DQ system is same as per phase of the 3-phase system, that is ABC system. The parameters are same, the variables are also same. So when converting from 3-phase to 2-phase, we don't have to change the variables or change the parameters. So in this case, you can see that this omega r can have various values, and accordingly we have so many systems. So if omega equal to 0, we call this to be a stationary reference frame. It is also known as Stanley reference frame by the name of a scientist called Stanley. Okay, so this can be employed in case of an induction machine, as you have seen little earlier that the induction machine was simulated in stationary reference frame. When the speed of the reference frame was 0, it was stationary in the space. Now if we take omega equal to omega r, the speed of the reference frame is same as the rotor speed, and we call this to be a rotor reference frame. And this actually will be useful when we model a synchronous machine. The reference frame is housed on the rotor, and hence we have certain advantage in case of an induction machine, and this is also called park reference frame. So we also call this as park reference frame. Now when omega equal to omega e, omega is the synchronous speed, we call the reference frame to be synchronously rotating reference frame or synchronous reference frame. So when omega equal to omega e, we call this to be synchronously rotating reference frame, or in brief we can call this to be a synchronous reference frame. And if omega is arbitrary, we call this reference frame to be an arbitrarily rotating reference frame or arbitrary reference frame. If omega is arbitrary, we call this to be a arbitrarily rotating reference frame. So we can recalculate this matrix. This is our transformation matrix. We can call this to be Ks or Cs. Now this matrix Ks is a function of theta. Now this theta 1 here is theta minus 2 pi by 3. Theta 2 in this case is theta plus 2 pi by 3. So it is basically phase shifted by 2 pi by 3 and phase shifted by 4 pi by 3 respectively. So we know this cos theta minus 2 pi by 3, cos theta plus 2 pi by 3. Similarly, we have the sine, and the third is corresponding to the zero sequence component. So we can always evaluate this transformation matrix, and depending upon the speed, if the speed is equal to 0, theta is the integration of the speed. Basically, this is the angle that it subtends, the d axis subtends with phase A. Now, if omega equal to 0, theta is equal to 0, and that's equal to theta r if omega equal to omega r, and that's equal to theta e if omega equal to omega e. So theta is the integration of the speed. Depending upon the speed, the theta is defined. If the speed is the rotor speed, theta is the rotor angle with respect to phase A of the stationary axis. If omega is the synchronous speed, theta is theta e, which is the synchronous reference frame angle or the angle of the synchronously rotating flux vector. So we can substitute the corresponding theta here depending upon whether it is a stationary frame or the rotor frame or synchronous rotating reference frame, and we can evaluate this transformation matrix, that is Ks, and when we have the transformation matrix, we can transform the ABC variable into dQo variable. Okay. So this is what we wanted to discuss here, and if you want to take the reverse transformation, we can also do that. It means if you want to calculate FA, FB, FC from FD, FQ and FO, we have to take the inverse of the matrix, and in this case the inverse of this matrix is the following. It is cos theta 1, cos theta 2 minus sin theta 1 minus sin theta 2, 1, 1 and 1. This is the inverse of Ks. It is the invertible matrix. So if you invert this matrix, we get Ks inverse, and Ks inverse is given as cos theta 1, cos theta 2 in the first column. Second column is minus sin theta 1, minus sin theta 2 and 1, 1, 1. We can verify that if we multiply K and Ks inverse, we get I matrix or the identity matrix. That can be verified. Okay. So with this background, we can just see if we simulate an induction machine in arbitrarily rotating reference frame, what would be the machine model. So we can do that. Induction machine model in arbitrary reference frame. So what we have here is the following. We have the rotor, we have the stator, and then we have the rotor windings, this is AS, BS, CS, AR, BR and CR, and is rotating at a speed of omega r, and we have taken a reference frame which is rotating arbitrarily. It means this reference frame is having D and Q axis. This is the D axis and this is the Q axis, and the speed of the reference frame is some arbitrary speed, that is omega radian per second. So if we model an induction machine in arbitrary reference frame, the stator variables will also have speed induced EMF. It means the actual machine is stationary. We have got AS, BS and CS, but the hypothetical or the virtual machine is rotating. It means this is my ds and this is the qs winding. As per the Cron primitive machine model, we have a 2-axis model in this case, but the axes are rotating at a speed of omega radian per second. And since the axes are rotating, the actual stator winding is stationary, but the dq windings are rotating in the space. And because of the rotation of the stator winding, there will be a rotationally induced EMF even in the stator, which is not usually present. And the rotationally induced EMF will be at a speed of omega. Omega is the speed of the reference frame. So we can write down the equation of the stator, that VDS is equal to RS IDS plus P psi ds, and that's not enough. In this case, the stator is rotating at a speed of omega. This winding ds is not stationary, it is in the rotating reference frame, and the speed of the reference frame is omega. So we have to have in this case a rotationally induced EMF, that is omega into psi qs. In a similar fashion, we can write down for the q axis vqs, that's equal to rs iqs plus p psi qs plus omega into psi ds, and in the rotor we will have the difference of the rotating reference frame speed and the rotor speed, because the rotor is also rotating at a speed of omega r, the reference frame is rotating at a speed of omega. The differential speed in this case is omega minus omega r, and the rotationally induced EMF will be appearing at a differential speed that's equal to omega minus omega r. So we can just write down the rotor equation, VDR equal to RR IDR plus P psi dr minus of omega minus omega r psi qr. These are all referred from the primary side, and hence we have the primed variable. VQR is equal to RR IQR plus P psi qr plus omega minus omega r into psi dr. So these are the 4 equations of the induction machine in arbitrary reference frame, where we have the rotationally induced EMF appearing both in the stator and also in the rotor. So we will now just write down the equivalent circuit of an induction machine in arbitrary reference frame. The equivalent circuit will be a DQ equivalent circuit, because we have the D axis stator and we have the D axis rotor here, DR, and we have the Q axis stator and also we have the Q axis rotor, and the reference frame is rotating at a speed of omega, as we have said before. And if we draw the equivalent circuit, we have to draw the DQ equivalent circuit in this case, and the equivalent circuit will be of this form. So we have this is the D axis circuit, so what we have in this case is, here we have VDS, RS, and this is our magnetizing inductance LM, and this is the stator leakage inductance, this is the rotor leakage inductance, this is the rotor resistance seen from the primary side, and we have the voltage source here, and that represents the rotationally induced EMF in the stator. In the rotor also will have a rotationally induced EMF. So in this case also we have a rotationally induced EMF in this case. So we have the rotationally induced EMF in this case, and then we have a resistance in the rotor. So this is the rotor resistance, and this is the stator current IDS, and this rotationally induced EMF we can see here, it is omega into psi qs in the D axis, and it is helping the applied voltage. So we can see if this is the applied voltage with plus and minus, this is minus and plus here, and this is omega into psi qs, and this rotational induced EMF in the rotor will be appearing as omega minus omega r into psi qr, and this sign we can also find out. So this current is IDR entering this kind of thing, entering the rotor circuit like this, and this will be minus here and plus here, and this is also helping the rotor applied voltage. Now in case of an induction machine, the rotor is short circuited, so we can say that VDR prime is equal to 0. The rotor is short circuited and hence VDR prime is equal to 0. So we have shorted the rotor in this case. Similarly, for the Q axis, we can write down the equivalent circuit. This is the Q axis equivalent circuit. Inductances are same for D and Q axis because we have a cylindrical structure. In an induction machine, the rotor is cylindrical, the stator is also cylindrical, the air gap is uniform, and hence the inductance of the D and Q axis are the same. So we can say here that we have the same RS in this case, we have the same LS, we have same LR, and we have the same RR here, and the sign of the rotational induced EMF will be different here, that is omega into psi ds, and here we have VQS, the Q axis applied voltage, and this is IQS, the Q axis current, and this current is IQR, the rotor current in the Q axis, and again VQR is equal to 0, and hence the rotor is short circuited. Now what are the various flux linkages? Now when we show here psi QS, this is the psi QS. The flux linkage in the Q axis stator. The flux linkage in the Q axis stator consists of the magnetizing flux and the stator leakage. This flux is the magnetizing flux associated with the rotor, the magnetizing inductance of the Q axis, and the flux associated with the leakage inductance of the Q axis is the Q axis leakage flux. So the magnetizing flux plus the leakage flux with the total flux linkage in the Q axis. Similarly, in the D axis, this flux linkage is psi ds, the stator D axis flux linkage, which consists of the magnetizing flux, which is associated with the magnetizing inductance, and the leakage flux, which is associated with the leakage inductance of the D axis. So this flux plus this flux with the total flux linkage in the D axis stator. Similarly, we can have the rotor D axis flux linkage is psi dr prime referred from the primary side, and then this is psi qr prime, the flux linkage in the rotor Q axis referred from the primary side. So this is the equivalent circuit of an induction machine in arbitrary reference frame, and if we take this equivalent circuit, we can simulate the machine both in the transient condition, also in the steady state condition, without any loss of accuracy. And we can get back the original current IA, IB and IC when we transform IDS, IQS and IOS by means of the transformation matrix into IA, IB and IC. So this finishes the modeling on induction machine. We have seen that the induction machine modeling is very interesting, and we have seen how the generalized theory of electric machine can be applied to simulate an induction machine in two-axis model. And there is an advantage we have already seen, that the two-axis model is simulated with less computational effort compared to a three-phase ABC model. And ABC model is much more complex compared to the two-axis model, and hence in many simulation method we go for the two-axis modeling of induction machine. Induction machine is called the workhorse of industry. About 60 to 70% of the motors are induction motors in industry. However, for very large power application, we go for synchronous motors, especially for application which are more than 1 megawatt or so, synchronous machines are preferred because of their design economy. So we will be discussing here the modeling of a 3-phase synchronous machine. Synchronous machine modeling is more complex than induction machine because it's a doubly excited system. We have 3-phase stator and we also have a field winding in the rotor. So if we see the structure of a synchronous machine, these are the stator windings AS, BS and CS, and we have the rotor here, and the rotor need not be a cylindrical rotor. Here we can also have a salient pole rotor. So we represent the rotor by means of a salient pole structure. So this is our rotor here. And the rotor has got the natural D axis. So we can call this to be the D axis. And perpendicular to this axis is the Q axis. So in the rotor we have windings on the rotor. The rotor has got the field winding and also the damper winding. So the field windings are here, and this is excited by a DC voltage source VF, and we also have the damper windings in the rotor. They are present in the D axis and Q axis respectively. So we have the D axis damper winding, which is sorted by bars, copper bars, and then we have the Q axis damper windings, which are also sorted, and they function like induction motor winding. So we have the field winding is called F, and the damper winding in the D axis is called KD. K stands for damper winding, and the damper winding in the Q axis is called KQ. So we have little complex situation. So instead of a cylindrical rotor, we have salient pole rotor, and the rotor has got DC windings as well as windings like induction motors, and they are called damper windings. So when we simulate this machine, we take the help of rotor reference frame. So what we will do here, we will choose the rotor reference frame for simulation, and this is also called Park reference frame, after the name of a scientist called Park. Now this reference frame is attached with the rotor. This is the rotor here. The rotor is rotating at a speed of omega r radian per second, and we assume that the phase sequence is ABC, is rotating from phase A to phase B to phase C, and the angle between phase A and the D axis is called the rotor angle, that is theta r. Now if you take the rotor reference frame, we have certain advantage. The advantages are as follows. When you take the rotor reference frame, the inductance matrix or the inductances of the synchronous machine, which are space dependent, becomes constant inductances, because in the D axis, this is the D axis, the air gap is constant. Air gap is always constant in the D axis. Similarly, in the Q axis, air gap is also constant, because the stator is cylindrical, rotor is salient pole rotor, but the D axis and the Q axis have well defined inductances, and we popularly say them as LD and LQ, or XD and XQ for the reactances in the D axis and the Q axis respectively. So if you take the rotor reference frame, there is a natural advantage of having constant inductance in the D and Q axis respectively. So in this case, the speed of the reference frame is the rotor reference frame, and if we write down the equation in the rotor reference frame, we can say that VDS is equal to RS IDS plus P psi ds minus omega R psi QS. VQS is equal to RS IQS plus P psi QS plus omega R into psi ds. Now what we are saying here is that we can have hypothetical winding here when we transform this ABC into DQ system. We are basically talking about a D axis winding here and a Q axis winding here. Okay. So the ABC windings are transformed into DS and QS, which are rotating in the space with the speed of the rotor. And when we find out the voltage of VDS and VQS, they are given by these two equations respectively. So this is the VDS, applied voltage in the D axis stator, and this is IDS. Similarly, for the Q axis, we can have the voltage, and this is the current IQS. So the ABC are transformed into VDS and VQS in the stator. Now what about the rotor? Rotor is already in the two axis model. You can see that the rotor is, we have definite D axis and definite Q axis, and in the D axis we have the field winding and the damper winding, and in the Q axis we have only the damper winding. So we can write down the equation directly for the field. VF is the field voltage, that's equal to RF IF plus P psi F. The rotor doesn't have any rotational induced EMF because the reference frame is attached with the rotor. So with respect to the rotor, the reference frame is not moving. So the relative velocity between the reference frame and the rotor is 0 because we have chosen rotor reference frame, and hence the rotor does not have any rotational induced EMF because the relative velocity is 0. Similarly, the damper winding KD is equal to RKD IKD plus P psi KD, no rotational induced EMF. VKQ is equal to RKQ IKQ plus P psi KQ, no rotational induced EMF. So we have 5 equations. Now if you compare this with the equation of induction machine, in induction machine we just had 4 equations: VDS, VQS, VDR and VQR. So naturally the simulation of synchronous machine is little more complex than that of an induction machine. Now let us try to see what exactly is the transformation here. Now if you choose in this case theta is equal to theta r, this is the transformation angle, because in this case the reference frame here is attached with the D axis. Now this is the reference frame angle, and we have assumed that omega equal to omega r, which means theta, the angle of the reference frame with respect to phase A of the stator, is equal to theta r. So if we substitute that here and write down our Ks matrix, the matrix for transformation, that's also equal to Cs matrix, we can say it is 2 by 3 of cos theta r, cos theta r1, cos theta r2, minus of sin theta r, minus sin theta r1, minus sin theta r2, half, half and half. So this is the transformation matrix which will transform the ABC variable of the stator into DQ variable which is in the rotor reference frame. And we can also write down the flux linkages. Psi ABCS is the flux linkage in the individual phase A, phase B, phase C. Now when we simulate the machine in the DQ reference frame, it is quite easy because we know that the inductance matrix is constant. The inductance in the D axis and the Q axis, they do not involve theta r. But what about the original equations? If you simulate in the actual ABC model, we can just go back to the the way we did for induction machine, what we did is the following, that we wrote down the equation VAS equal to RS IAS plus P psi AS. This is simulation from the first principle. And similarly, VBS is equal to RS IBS plus P psi BS. And similarly, we wrote down for the C phase RS ICS plus P psi CS. Now we have 3 phases and 3 equations, and we also have VF, that's equal to RF IF plus P psi F. VKD is equal to RKD IKD plus P psi KD, and VKQ is equal to RKQ IKQ plus P psi KQ. Now these equations represent the equation of the actual synchronous machine in 3 phase ABC, and this is little more involved because we have 1, 2, 3, 4, 5, 6 equations, and we have to solve 6 differential equations, which is more complex. Not only that, the flux linkage here psi AA, psi BS, psi CS will involve the inductance matrix and the currents IA, IB and IC, or IAS, IBS and ICS, and the inductance matrix will be a function of theta r because of the saliency. So we will see in the next lecture how we can transform these equations into DQ equation in the rotor reference frame, and as a result of that, the inductance matrix, which we will see in the next lecture, which is a function of theta r, will be independent of theta r, and which is an advantage of simulating a synchronous machine in rotor reference frame.